SwayamPrabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will continue our discussions on vapor absorption refrigeration systems. In vapor absorption refrigeration systems, there has to be a refrigerant and one absorbent. Refrigerant is absorbed by the absorbent at lower temperature, and then this is absorber, and then it goes to generator where the mixture is heated and refrigerant is liberated. During this process, the pressure of mixture is also increased. Pressure of the mixture is also increased with the help of a pump, and sometimes difference in elevation also used for increasing the pressure. In that case, the generator will be below the absorber. Now, there are certain combinations of different compounds like ammonia water. Ammonia has very good affinity with water. So, ammonia is a refrigerant and water is absorber, that is another type of combination can be, which is very popular, is lithium, here water is a refrigerant and lithium bromide is absorbent. So, these two type of combinations of vapor absorption refrigeration, there are many other combinations also, but these two combinations are very popular. Now, we will take them one by one. Let us start with the ammonia water system. In ammonia water system, because it is this combination is taken because ammonia is a refrigerant and water is an absorbent, because they have very strong affinity to each other, water and ammonia. Two are mutually soluble for a wide range of operating conditions, especially existing inside the system. Both are highly stable and compatible with most of the material found in the refrigeration system, except copper. Copper is not compatible with ammonia. So, wherever ammonia is used, copper fittings are not used. Now, I will draw arrangements in a ammonia water refrigeration system. So, we will start with the absorber. The system has one absorber where weak ammonia solution exists. So, this is an absorber where absorption of ammonia takes place in weak solution and it becomes a strong solution. During this process, heat is liberated, that is why cooling water is circulated in the absorber. Now, the vapor to absorber, it comes from evaporator. It is a normal evaporator. From evaporator, the vapor goes to absorber, and vapor gets absorbed here. Now, this absorbed vapor, the pressure of this absorbed vapor has to be increased, normally 10 times, with the help of a pump, and there is a generator. There is a generator in the system. Now, refrigerant is pumped to the generator with the help of a small pump. Now, when the refrigerator comes to the generator, I mean the absorb this ammonia water mixture, when it comes to the generator, the heat is supplied to the generator. Now, this heat may be a waste heat or heat from a back pressure turbine or waste heat of any process. some waste heat from the gas turbine or any waste heat will do. So, this waste heat heats this mixture in generator and ammonia is liberated, and in fact it has traces of water also. So, the trace ammonia with the traces of water, it goes to the rectifier. In rectifier, the water is separated out and it is drained back to the generator, so that at the exit of the rectifier we get pure ammonia. So, I am repeating the processes. This is as evaporator, absorber, generator. Now, we have come to the rectifier. Now, this ammonia after rectifier, it goes to the condenser and condensation takes place. So, at this point we have, at the exit of the condenser, we have high pressure liquid with low temperature. That normally happens in vapor compression system, and after that expansion of this ammonia takes place. This is anhydrous ammonia and then after expansion it enters the evaporator, and the cycle is not complete yet. Cycle is not complete yet because liquid is pumped from absorber to generator. After certain period of operation, all the fluid from absorber will be shifted to the generator and generator will be full. So, there is a drain back arrangement again, and the valve is provided to meet the pressure difference. So, pressure is dropped across the wall, and the weak solution, it is called weak solution because the ammonia has already been liberated from the solution, but it still consists some part of the ammonia. So, this is weak solution from generator enters the absorber. Absorber gets ammonia from evaporator and it makes the solution rich, and rich solution is pumped back to the generator. So, this is one cycle which keeps on going, and after that the vapor after rectifier they go to the condenser as in the case of vapor compression system, and then after expansion the vapor goes to the evaporator where refrigerating effect takes place. Now, in order to increase the efficiency of the system, because we can provide one or two heat exchanger which can improve the efficiency of the system. The system efficiency can be improved. Say this, suppose this condenser vapor, this is expansion valve, I will put somewhere here. This condenser vapor, let us say it is at 40 degree centigrade, and this evaporator vapor may be around, let us say minus 10 degree centigrade, and in any case it is going to get heated here during this process. So, a heat exchanger can be provided. So, instead of directly going to the absorber, it passes through a heat exchanger and then it goes to the absorber, and this heat exchanger is provided to facilitate heat exchange between these two fluids. This is at 40 degree centigrade, this is at let us say minus 10 or 0 degree centigrade. Heat exchange takes place, vapor gets superheated and the liquid gets subcooled. When subcooled liquid is expanded, we get more refrigerating effect. At the same time, this heated, suppose after attaining heat it becomes 0 degree centigrade ammonia. So, this 0 degree centigrade ammonia or superheated ammonia vapor, it goes to the absorber, it gets absorbed here. Now, in this side of the system also there is a scope for improvement, because the fluid which is going up and fluid which is going down, they are at different temperatures. So, here suppose I shift this expansion valve to here and pump somewhere here. A heat exchange can be arranged between these two fluids, because in absorber in any case heat has to be removed. So, if heat is removed here, right, heat is removed here. So, here load will reduce. This heat, this high temperature fluid this heat will be used for heating this fluid. This is solution of absorber and absorbent or which is pumped to the generator. So, in any case it is going to get heated here. So, with the return line, if it takes heat, that will also improve the efficiency of the system. So, this is a typical arrangement for ammonia water system, which is in the presentation it is shown here. Now, I will take one example again. Suppose for absorption refrigeration system, the following data refer to vapor absorption refrigeration system, where evaporator temperature is minus 15 degrees centigrade, and that is 258 Kelvin. Generator temperature is 120 degrees centigrade, that is equal to 393 Kelvin, and absorption temperature is 40 degrees centigrade or 313 Kelvin. Now, with these temperatures, suppose in this ammonia type of system, so this heating temperature in generator is 120 degrees centigrade, evaporator temperature is minus 15 degrees centigrade. So, let us make it minus 15, and this absorber temperature is 313 Kelvin. If I want to find COP of the system, COP of the system will be evaporator temperature T absorber minus T evaporator, T generator minus T absorber by T generator. If I put the respective values, it is going to be equal to 258 divided by 313 minus 258 multiplied by 393 minus 313 divided by 313, and the COP I am going to get is 0.9545. COP of absorption system is close to 1, I mean 0.7, 0.8, 1 is very good. If you compare the COP of the vapor compression system, the COP is 3.5, 3.5, and it go up to 3.75. So, it does not mean that the COP of the absorption system is very, very low. In fact, what happens in absorption system, we are using only heat. In vapor compression system, energy input is in the form of work, which is high grade energy, and this high grade energy is converted from the low grade energy. Perhaps the efficiency of that device, or maybe some engine or turbine, steam turbine, the efficiency of the conversion may be 30, 40 or 50%. So, that we do not take into the account. If we take that into account, then these COP of 1 of absorption system is comparable with the COP of 3 in case of vapor compression system. And the benefit of absorption system is, if the waste heat is available, then we are getting the refrigerating effect with almost negligible expense of energy. So, here the COP is 0.9545, but the actual COP is 60, because in actual cycle 40% losses are there. So, actual COP is 60%. So, actual COP is COP dash, it is 60% of this, it becomes 5727. Here 10 tons of refrigeration system has to be given. So, 10 TR means, sorry, 100 tons of refrigeration. So, 100 tons of refrigeration means 100 into 3.5 kilowatt. This much of energy is required, and this much of energy is required for steam at 130 degrees centigrade. Suppose steam is used for heating at 130 degrees centigrade. We can assume that steam is condensing here, and mass of the steam is the energy supplied, and that is, so mass of the steam can be calculated as, because COP is refrigerating effect, that is 100 into 3.5, and mass of the steam multiplied by Hg minus HL, I mean enthalpy of saturated steam. So, M is equal to 350 divided by COP is 0.5727 multiplied by 2720.8 minus 546.38. This is 2720.8 is the enthalpy of saturated steam at 120 degrees centigrade, and this is enthalpy of saturated liquid water at 120 degrees centigrade, and this gives the mass value as mass flow rate as 0.28115 kg per second, or mass flow rate is 16.87 kg per minute. So, this is the amount of steam which is required here to produce minus 15 degree centigrade temperature here. Now, after this there is another combination of absorber and refrigerant, that is water and lithium bromide. In this system, water ammonia system, water is absorbent, ammonia is refrigerant. Now, here in this system, the water is lithium bromide type of system, the water is refrigerant and lithium bromide is absorbent. Now, this system, lithium bromide water system, works on a very low pressure, and in different books you will find different type of arrangements. It has 4 drum arrangement, 1 drum arrangement, 2 drum arrangement is also there. But in order to understand the system, this lithium bromide water refrigeration system, 2 drum arrangement is best suited, because in 2 drums arrangement we take low pressure drum and high pressure drum. Because in a vapor compression system also, if you look at the vapor compression system, there is always a high pressure side and low pressure side. This is low pressure side, evaporator. After expansion, it is a low pressure side, and this is high pressure side. And this condenser, and after the compressor, it is a high pressure side. And pressure increases in compressor, pressure reduces in expansion device. Now, here in absorption system, lithium bromide water absorption system, water lithium bromide absorption system, where water works as a refrigerant. Now, this is a high pressure vessel, this is a low pressure vessel. In a high pressure vessel, suppose water vapor is condensed in high pressure vessel. We will start from condenser. So, there is a cooling water, I will show with the blue ink, so it will be easy to understand. So, this is water, chilled water which flows here, and water vapor is condensed, and water vapor is collected in this tray. After collection in the tray, the water vapor, I will shift this a little below. The water vapor goes to the evaporator through expansion valve. Now, after expansion, as we know, we get low temperature, low pressure vapor, that is water vapor, and there is a pipeline for chilled water. So, this is a pipeline for chilled water, and chilled water, this is chilled water. So, chilled water is circulated in this pipeline. So, the low temperature water vapor, when it comes into contact with this pipe, right, heat is taken away by the water, and that is how the temperature of chilled water is of the water circulated in this pipe is reduced. Now, again that this part is absorber. Now, absorber and generator, there are two things. Now, water gets absorbed in the absorber, this is absorber. From the absorber, there is a pump, and this rich solution is pumped to the high pressure side, where heating takes place. Now, heating here can be done with some external means. Now, heating takes place here, and after heating the water vapor is generated, and this vapor gets condensed here in the condenser, and this condensed vapor is expanded through a valve. It goes to the evaporator where chilling of water takes place. The remaining water is absorbed in the absorber. So, in absorber also we have to provide some cooling water in absorber. After absorber, a pump is used. The function of the pump is to pump the low pressure liquid to the high pressure liquid. This is rich solution. Rich solution goes to the generator. This is generator, and in generator the vapor is generated. Again here we have to take care that if we do not provide drain back arrangement, then all the rich solution will be shifted to the generator. So, a drain back arrangement is again provided here through an expansion valve. The lean solution of water in lithium bromide is expanded and it comes to the absorber. And it does not come from here, it has to come from below in the form of spray. This is the actual arrangement. Now, further in order to improve the efficiency, because here anyway it is going to get heated, if we can, and this is if we can heat here by providing a heat exchanger. So, this is a high temperature fluid, this is a comparatively low temperature fluid. If heat exchange takes place here, in that case the temperature of lean solution before the expansion valve will be less. So, we will be getting less and less temperature here. At the same time when the fluid is pumped, when the vapor is going to the generator, anyway heat is going to be added here, but we get some additional amount of heat here. This is arrangement for further improving the performance of the system. Now, here in this system water is used in 3 modes. Water is used as a refrigerant in the entire cycle. Water is used as a secondary refrigerant. Water is used as a secondary refrigerant because this chilled water goes to the building or some cooling place, takes heat from there and come back to this place. So, water is also a secondary refrigerant, water is also a main refrigerant, and water is also used as a coolant. So, water in this cycle, water is used for 3 purposes. Now, in this cycle, the best part is in an ideal cycle, in ideal combination, in ideal mixture combination, the difference between the boiling point should be around 200 degrees centigrade. But here it is much more in case of lithium bromide and water system. In case of if you compare the normal boiling point of ammonia and water, the normal boiling point of water is 100 degrees centigrade, normal boiling point of ammonia is minus 33.33 degrees centigrade. So, difference is 133. That is why when the vapor emerges from generator in case of ammonia refrigeration system, it has some traces of water. But in lithium bromide type of system, when heating is done, there are no traces of lithium bromide. Pure water we are getting here in the condenser, which gets expanded here. Now, the limitation of the system is because water is a refrigerant, it should not be operated below 0 degree centigrade, or this system is not useful for the operation below 0 degree centigrade. But high temperature applications it is extensively used, and the pressure inside the vessel, here the pressure is approximately, vacuum is 93 kilopascal and here is vacuum is approximately 99 kilopascal. So, system work in very high vacuum. Vacuum means pressure below the atmospheric pressure. If atmospheric pressure is say let us say 97 atmospheric pressure. So, 99 3 vacuum means it has only 4 kilopascal absolute pressure. 93 kilopascal vacuum and it has only 4 kilopascal absolute pressure. And here you can see 99 kilopascal, it is almost 0, vacuum is very high. Here in this case it is not possible. Here the vacuum will be of the order of 96. So, in the evaporator the pressure is approximately 1 kilopascal or 1.5 kilopascal. Absolute pressure here turns out to be around 0.6 to 1.2 kilopascal, and here absolute pressure is approximately 6 to 7 kilopascal. So, system works in a very high vacuum, that is one thing we have to maintain, but COP of the system is approximately 0.7. Third thing is, in any part of the system the temperature should not exceed 120 degrees centigrade in order to avoid corrosion in the system. This system is best suited for solar energy, because if solar energy is used as a heat source, solar thermal energy is used as a heat source, then we can run this type of system in order to provide solar cooling. Normally solar energy is for heating systems, but here with the help of absorption systems, the solar energy can also be used for cooling purpose. So, overall working pressure in lithium bromide system is barely above 0.15. There is no fear of bursting because the pressure is very low. Water is non-toxic, therefore can be used directly. Negligible energy for pumping is required. Here for the purpose of pumping, negligible energy is required. A small pressure difference leads to elimination of pump. If the small pressure difference is there, we can swap these cylinders, and then in that case the pump can be eliminated. So, this is how this cycle can be compared or has advantages over water ammonia cycle. That is all for today. In the next class, we will continue with the vapor absorption systems. Thank you.